So, we were discussing our boundary layer theory, and towards the end of our lecture, we had said that when you have your dimensionless Navier-Stokes equations, plus 1 by Re del square u. So, these dimensionless Navier-Stokes equations were derived. So, this Re was Rel. They were derived by assuming this, and this doesn't hold. This gives you, so in limit of Rel much greater than 1, when you derive the equation, you get the inviscid equation, and that doesn't hold for the equation doesn't hold for inner region. So you get an outer region solution. So you get, let's say, you get an equation that is valid in region 2, and after that what you have is basically you have to rescale your y coordinate. So rescale the y coordinate. So we formulated that y star should be y by delta, or we said that the length scale in y direction is delta, the correct length scale in y direction is delta, and then we derived the inner layer equations. Okay, we derived the inner layer equations as, so if you look at the dimensionless form, we had del u star over del x star plus del v star over del y star equals 0, right? And then we had u star del u star over del x star plus v star del u star over del y star equals minus dp star over dx star plus del square u star over del y star square. Okay. So this is what we had. And then we said that this dp dx, basically pressure in region 2. So P star in region 2 is equal to P star in region 3, because we had derived from y momentum equation that this is 0. So for a given x location, if you go from y in region 2 to y in region 3, if you come downwards, if you come close to the wall, then you will see no change in pressure as you move from 2 to 3. Okay, as you move from 2 to 3, you will not see any change in pressure. So within the boundary layer, the pressure is constant in y direction, could be changing in x, and we said that that change in x we derive from the outer layer equations. So we know that pressure in region 2 varies as u in minus u infinity star d u infinity star over dx star. So this u infinity star is basically u infinity by the so it's basically u by u infinity. Okay, so this is this u infinity star is basically u star for x star and y star tending to infinity. And remember, u star is u of this by u infinity. Okay, so u infinity star is 1 for 0 pressure gradient, 0 pressure gradient, flat plate, boundary layer. Okay, for 0 pressure gradient, flat plate, boundary layer, u infinity star is 1, and dp2 star by dx star is this. Okay, and from here we note that we can substitute it in our boundary layer equation and we obtain this. Just keep it here. Okay, and then we we said that for zero pressure gradient flat plate boundary layers, this guy is 0, and we arrived at a simplified equation combined with our continuity equation. Okay, and then we were setting out to convert this into an ODE. What were the boundary conditions? The boundary conditions were u star for x star tending to 0, y star is 1, u star for x star, y star tending to infinity is 1. So, this is moving in this direction close to the leading edge. So, this was leading edge, and this is up in the free stream. And then we had u star x star comma y star equals 0 because of no slip, and then v star x star y star equals 0 is 0 due to hard wall. Okay. So, from here onwards, at least as far as Blasius this equation is concerned, so this is also, this is not known as Blasius equation. As far as our flat plate boundary layer is concerned, I am going to drop the stars. Okay, just for my convenience of writing, I am going to drop the stars. So, drop these stars. Okay, and what I am going to do is I am going to write that, or I am going to say that we expect a self similarity solution. We expect self similarity because there is no imposed external length scale in the flow. Okay, if you go back to our discussion on an impulsively moving plate, we said that there is fluid on top of it and there is a plate that is moving impulsively. So, in that we said that we expect a self similarity solution because there is no externally imposed length scale in the flow. Okay. Here also you have a very similar situation where your plate is not moving in impulsively, but you have flow, you have steady flow that is going past the plate. The plate is technically, we are not concerned about the length of the plate, we are not concerned about the length of the plate, we are just concerned that we are looking at this outer regime in x and inner regime in y. As long as we maintain those restrictions, remember the restrictions were that x, or actually they are still not, yeah, we have derived those. So, if this is L and this is delta, then we have derived that delta by L is 1 by square root of REL, and we are working in the limit of REL much greater than 1. So, as long as we satisfy these conditions, we are not bothered about any lengths that are imposed by the geometry of the flow. It is a flat plate, there is no other length that we are concerned with. So, we expect a self similarity solution. Now, again, this is not a conclusive proof that there is a self similarity solution. The only way to prove that there is a self similarity solution is assume that it exists, carry on with your derivation. If we reach a closed system of equations, then our assumption was true. So, the only way to disprove self similarity is through contradiction. Okay, the only way to disprove self similarity is through contradiction as far as this course is concerned. So, if I ask you that assume self similarity, you can just take it as, accept it as truth and proceed forward in the exams. So, we expect a self similarity. So, what I am going to say is that u star, let us say, is some g of eta, where this eta is the similarity variable called y, y over some, okay, I am dropping the stars, no, so it's u only, y over some delta of x. Okay, so this delta of x is some function. Okay, this delta of x is some function. If you recall, in our impulsively moving plate we had y over square root of nu t, right, we had y over square root of nu t. We will have some delta of x under which the self similarity will be valid, and we will derive that just now. So assuming this, we can formulate the, we can substitute basically this into our governing equation and derive the results. So u being g of eta, we have del u by del x as g prime. So g prime means d by d eta. Okay, prime I'm going to represent for d by d eta. So del u by del x is g prime times del eta over del x, which is g prime and then minus y over delta square d delta over dx. Okay, and I can also write it as minus g prime eta 1 by delta d delta over dx. So from continuity, we know that del v by del y should be equal to minus del u by del x, which is minus of this guy. So g prime eta 1 by delta d delta over dx. Okay, I can change the variables on left hand side by writing it as some del v by del eta and then writing it as del eta over del y. This makes the integration easier. So del eta by del y is what? Eta is y by delta x. So del eta by del y is 1 by delta x. Okay. So 1 by delta x, I take it here and multiply. So del v over del eta is simply g prime eta d delta over dx. So from here I get that v is going to be, so we take out the d delta over dx outside and then we have, yeah, and then we have g prime eta d eta. So we apply the by parts formula. So we have v is d delta over dx integral g prime times eta d eta. So applying the by parts there, we will get eta of g, or yeah, is it eta of g, and then a minus of integral of g d eta. Yeah. Okay, so here instead of carrying this integral of g eta, I am going to say that f, let's assume some f which is this integral of g eta. So this formula simplifies to d delta over dx eta f prime. So if this is true, then g is f prime minus f. Okay, now knowing this u, we can also write what is del u by del y. Del u by del y is simply g prime del eta by del y, which is g prime by delta of x. We know g prime is f double prime. We can also compute del to u by del y square, which is going to be simply f triple prime over delta square x. It's good to switch it off, no? No, I think you switched off. All of them are connected. Then you can switch it on. I think I can tolerate that for a lecture. It's okay. And then now we substitute that in our momentum equation. So u times delta u del u by del x. So del u by del x was this. Let's write it in f. So that is 1 by delta d delta over dx. G prime is f double prime. So minus of f double prime times eta. Okay. So u times del u by del x is, u is f prime. So minus 1 by delta d delta over dx f prime f double prime eta, and then v times del u by del y. V is this, del u by del y is that f double prime by delta x. So we have f double prime by delta Okay, and you will see simplifications happening very quickly now. And then we have del 2 u by del y square, which is simply that guy, f triple prime over delta square. So these two cancel out. Okay, luckily some simplification is occurring in the algebra. These two cancel out, and then we are left with, so I can take this on that side, and I am left with f triple prime and multiply with delta square plus delta d delta over dx times f double prime equals 0. Okay. Now notice this is purely a function of eta. F triple prime is purely a function of eta. F double prime is also purely a function of eta. The only way this equation can be an ODE is if this is constant, or in other words, the only way our self similar solution is a or solution exists if delta d delta over dx is some arbitrary constant. That is the only way this equation is an ODE. Okay. And this is a very good check of looking at your equation, and if you had some other terms, let us say you had some other coefficient here, and if you keep one constant the other cannot be constant, that means there is a problem here. So, as I said, everything about self similarity is unfortunately an iterative process. It is very hard, I mean eventually these are nonlinear PDEs. Okay, we do not have any general theory for nonlinear PDEs that can help us find the closed form solution. One technique exists, but that is a little iterative in the sense that you assume something, you check if that can be possible, if not then you have to either make changes here or you have to completely drop the notion of self similarity. Okay. If you take advanced classes in PDEs, then you will know that there are some checks which you can do a priori to at least help you reach this conclusion. Okay. You can eliminate if self similarity cannot exist before doing all of this, but that is not part of this course. We will just say, as far as this course is concerned, that you can assume something on velocity, carry out this algebra, and if you can derive a condition which is satisfied by every coefficient and your nothing is violated, there is no contradiction, then you can be satisfied that self similarity exists. So, if this exists, that means what can we say about delta? Delta is square root of 2 c x. Okay. Delta is square root of 2 c x, and the equation is f triple prime plus c f double prime equals 0. This is called the Blasius equation. This is called the Blasius equation, after a person obviously Blasius who derived this first, and we are halfway there. Okay. We are still not full way there in concluding that a self similarity solution exists. We have concluded that I can convert this PDE to an ODE. We have concluded that I can convert this PDE to an ODE. We have to be careful about the boundary conditions also. Okay. Luckily it works out for us in this case, and that is if you have eta, which is y over square root of 2 c x, then we note that for both y tends to infinity and x tends to 0 individually, we have eta tends to infinity, and both of the conditions will give us that f prime eta tends to infinity equals 1. So, both of these conditions give us this. So, two boundary conditions effectively have collapsed into a single boundary condition for f or f prime. Okay. What about this one? This one gives us that f prime eta equals 0 is 0. Okay. this one gives us f prime eta equals 0 is 0. So, if f prime eta equals 0 is 0 and this is also 0 at eta equals 0, f prime is 0. So, f has to be 0, and you will see that f prime did not really have to be 0 for f being 0, because you have an eta multiplying it and you are calculating this at eta equals 0. Okay. So, this guy gave us this, and v star equals 0 gives us this, and now we are at our final point where we can conclude that okay, a self similar solution exists to this equation. Okay. Yeah. Yeah, we need this for a self similar solution to exist. There is no requirement for self similar solution to exist, and notice that this is a non-linear PDE. There are multiple solutions. So, we are finding one solution that happens to hold physically and also validate experiments. Yeah, that's a very big simplification that happened for us. If the two conditions don't collapse into one, okay, then you will end up with a over constrained system, not a closed system. Then yes, the whole assumption to begin with was wrong. Maybe you may have to change something here, as we will see as we go further. You may have to change something here. Okay, there are some self similarity guesses that we can make. So, we can introduce some other functions. For example, as we go further down and we look at jets and mixing layers, we will see that you can assume something like this. Okay, u is fx times g eta, and you can find this fx and delta x. So, you will have two coefficients involving f and delta, and if you fix those two as constants, then you will derive some conditions. Okay. So, you cannot straight ahead, you should not straight ahead dismiss that self similar solution does not exist, but you can safely conclude that this form of self similar solution does not exist. Okay. The self similarity is, instead of u being similar, u by fx is similar, u by fx is self similar. Okay. And that requires, as I said, iteration. You need to look at your boundary conditions and see if all of them collapse into one, into the closed set. So, this gives us a solution, and actually the solution can be computed. Okay. We cannot solve this, we cannot solve this ODE or this one analytically. We can compute the solutions, either we do a series approximation, we can do series approximation. That is not a very good thing to do in this case of nonlinear ODE, and you can read about it in the textbook, or you can just go ahead and compute the solution numerically. So, if you want to compute the solution numerically, maybe some of you have seen which kind of a problem is this. How do we solve these ODEs numerically? How do we solve these ODEs? If I have to solve an ODE numerically, how do we do this? Okay, so how will you do this? How will you solve it using finite differences? Okay, but then you have, so you will end up with some non-linear system, and so you want to solve it as a boundary value problem. You want to solve it as a boundary value problem. You can try doing that and see if it gives you a result. The usual way to go about these kind of equations is doing the initial value problem type of a marching system. So, you convert this third order ODE into a system of 3 first order ODEs, you say that my f prime is some f1, f1 prime is some f2, and f2 prime, which is f1 double prime or f triple prime, is minus of c f times f double prime, which is f1 prime. Okay. So, this way you have converted your system, your equation into 3 first order ODEs, and then you assume some values of these at eta equals 0. Remember, we do not have all of them at eta equal to 0. You will have to assume some value for f double prime at eta equal to 0 and start marching for a large value of eta, and this is called the shooting method. I do not know if you know this. So, we can use the shooting method to solve this equation. Have you covered this in any of your numerical courses? Shooting method has not been covered. Are you guys aware of Rangekatta integration? Huh? So, that is what you use to do the marching, starting from eta equals 0. Starting from eta equal to 0, you define some large eta and you march in eta for large values of eta. And then you have to check your boundary condition. But if you don't know shooting method, maybe we can have some extra lecture to discuss that later on. Okay. So, you can solve this equation and eventually what you will get is something like this. So, you will have this as, let us say, f prime, and this is eta. So, remember, f prime is this value of velocity. So, it will look something like this. Okay. And for about eta around 1, depending on what constant you take there as c, around eta equals 1 for c equals to 1, you will see that your velocity is more or less equal to 1 or equal to free stream. Remember, all of this was dimensionless. Okay. So, your velocity is almost equal to free stream. And what is the physical way of thinking about it? The physical way of thinking about this self similarity solution is that you have some velocity profile here in x and y. So, this is in x and y. So, let us say you have these velocity profiles, and what you can do is at different x stations you can define these profiles, and instead of plotting as u x comma y versus y for different x, let us say, instead of plotting it like this. Okay. So, you will have, let us say, if you plot it for different x, how will it look? It will look something like this, right? Okay. If you go back to your impulsively moving plate, this is how the solution plot looked like in time. Okay. Now, this is how it looks like as you are moving further downstream. So, instead of plotting it versus y, you can do a scaling of y and say this is, let us say, some constant times x, square root of some constant times x. You can do a scaling, and instead of plotting u, you can plot u by u infinity, and here you have 1, and all of them, if you do an experiment, let us say, if you do an experiment for flow past a flat plate, and let us say you measure velocity here, here, you measure velocity here, you measure velocity here, all of those points will fall on the single curve once you do the scaling of your y coordinate. And that is actually the very good experimental proof for your self similarity. Okay, that is a very good experimental proof for your self similarity when you are able to collapse your experimental data into a single curve. Okay, and that is useful. That is useful how? Because to characterize your boundary layer, if you can do a collapse, that means you do not have to make measurements for different x values. If you have made measurements at a particular x value, using that you can compute what will be the what will be velocity at other x values by saying that, okay, if I keep y by square root of x as constant, then the value of u is going to remain constant. and that is very powerful. Basically, this is like non-dimensionalization, where you have found a very good non-dimensionalization for your solution. So, instead of doing an experiment where you take hundreds of measurements at x locations, you just take measurements at single x location. Okay. And if you have a proof of self similarity a priori, then you can use that. Okay. Now, let us address one of the major simplification that we made in this, and that was your pressure is varying like this. Okay, basically pressure is varying like this. That's not an assumption. We said that for zero pressure gradient we are going to ignore pressures. Okay, but whenever we look at flow past any, I can get rid of this algebra. Whenever you look at flow past any bodies, okay, whenever we look at flow past any bodies, let us say you are looking at flow past some airfoil. Now, if you look at this, you have a flow coming and hitting on the airfoil, and then these flow streamlines are going to go something like this, let us say. So, the idea is when your flow is going over these curved surfaces, your u infinity, or basically this u infinity star, is not constant. And if you recall our potential flow solution past a wedge, okay, we had taken what, pi by m, let us say, and we had obtained that your phi, the flow potential, is some constant times, what was it, r to the power m cos m theta, something like this. Okay. So, now from here, if you compute your u r and u theta and you combine them to make a u x comma u y, and let us say I take this m as something greater than 2, something smaller than 2. So, when I take it something smaller than 2, I am taking a condition like this. The angle is greater than pi by 2. When m is smaller than 2, I am taking angle to be greater than pi by 2. So, the case is something like this. So, when you have a flow that is turning at an acute angle, here the flow itself is turning at an obtuse angle, the flow here is turning at an acute angle, right. You can look at this situation something very similar to as this, and this is known as flow past a ramp. You have a flow coming in here and it is getting turned by an acute angle as the flow moves past a ramp, and here we will see that your ux and uy, essentially this ux will be proportional to some x to the power alpha. It will have a power law. This x ux will have a power law for your flow past a ramp. You can confirm this from this. Basically, solve the system for m greater than 2 and convert it into x and y velocities. Okay. And in these cases, of course, your u infinity star is not a constant, which means your dp star over dx star is not 0. So, you do have some pressure gradients. You do have some pressure gradients. Now, what do these pressure gradients do? And this is what our demonstration is also going to be about. What do these pressure gradients do? And that is where exactly the shortcomings of your inviscid theory come, and that is where we transition sort of historically from aerodynamic development from inviscid theory to aerodynamic development, which is informed from both inviscid theory and boundary layer theory. Because something that we discuss just now and what we are going to see in a moment is not it cannot be captured by our inviscid theory, and it is indeed important when you look at flow path shapes which induce a variation in velocity. let us look at what happens when you have a pressure gradient like this. So, recall our governing equation here. So, again I am dropping all the stars. Okay. So, u del u by del x plus v del u by del y equals minus dp over dx plus del 2 u over del y square. At wall, irrespective of wall being curved or not, we know at wall u and v both are going to be 0, right. Even if it is curved, we know tangential and normal direction velocity overall, all components are 0. If we can show that tangential and normal direction velocity are 0, these are two orthogonal components. If they are 0, all components are 0. So, velocity is 0 at the wall, irrespective of the wall being curved or not, due to no slip and hard wall. So, if that is the case and you substitute it in the governing equation, you see at wall dp dx equals del to u over del y square. At wall dp dx equals del to u over del y square. Okay. Now, you can say that your shear stress at the wall, dimensionless shear stress at the wall is del u by del y. Notice that at the wall, this is dimensionless shear stress. Okay. So, if you formulate a dimensional shear stress, then you will need viscosity also. Since I am working with all dimensionless variables, so this is dimensionless shear stress, and that is equal to del u by del y at the wall. So, this means dp by dx is del tau w over del y at the wall. So, this has very important conclusions, or if you do not want to think about it in terms of shear stress, you can still look at it in second derivative terms, and let us look at what are the implications. So, let us say you have a curved face like this, okay, and as it happens, so this is something you can confirm when you solve for flow past a cylinder, inviscid flow past a cylinder. You can show that pressure, basically pressure decreases on this side of the cylinder and pressure increases on this side of the cylinder. And for many curved faces, this is exactly how it behaves, that as you move further downstream till your apex, the pressure decreases and then the pressure starts to increase. So, when your pressure is decreasing, dp by dx is what? Negative. As you are moving further downstream, pressure is decreasing. So, dp by dx is negative. So, if dp by dx is negative, then del to u by del y square is negative. Second derivative being negative, what does it mean? Hmm? What? No, I mean something more. dp dx being, so what can you say about the variation of velocity? Second derivative, we are not saying del u by del y is 0. Okay, there is no maxima minima thing yet. We are not saying tau w is 0 at the wall. Shear stress can't be 0 at the wall. So, del 2 by del y square is basically del 2 u by del y square is negative. Hmm? So, what does it mean in terms of, let us say, concave upward or concave downward? What can you say? What can you say? So, del 2 u by del y square is negative. So, du by dy is decreasing as you move away in y. So, du by dy is decreasing as you move away in y. So, it will be something like this. Your velocity, let us say this is your y, the velocity will be varying such that the derivative du by dy is approaching 0 from a very large value to 0. Okay. As you move further, this is what happens to your du by dy. Now, let us say we reach a position where dp by dx is now, so pressure is increasing. So, dp by dx is actually greater than 0. What happens to dp by dx greater than 0? Del to u by del y square is greater than 0. So, at the wall the derivative is actually first increasing. At the wall you will see the normal derivative of velocity will first increase, okay, and then it will start to decrease because eventually it has to go to free stream velocity which is constant. Eventually it has to go to a free stream velocity which is constant, and if you keep moving further downstream in this kind of a situation, what you see is after certain moment you will see this happening, that your velocity will reverse. Your velocity starts to reverse, okay, because when your del 2 u by del y square becomes very highly positive, this is exactly how it behaves, okay. And this, when it has happened, so technically it will reach a point where this is exactly 0, del 2 u by del y square is exactly 0. So there is an inflection point here, and then this is moving like this, okay, and after this point it will move to this kind of a variation, and this point where del 2 u by del y square is 0 and after that it is becoming positive, that is called the separation point. So basically if you look at the boundary layer, what has happened is, if you looked at the boundary layer that was forming, what has happened is, so this was how the flow was going, and then suddenly there is a reversal of the flow. So you will see that there is a reversal of the flow that happens and your boundary layer has separated from the from the plate or from the curved surface or boundary, whatever it is. And this boundary layer separation is the cause of major problems in all of aerodynamics. You don't want your boundary layer to separate. If you want it to separate, you want it to separate very reliably. You don't want to bank on the unsteadiness of the flow that results from this boundary layer separation, okay, which is something that you may learn later on in the course, and this is something that we can show as a demonstration very clearly. So let us say I'm looking at, so this is a small wind tunnel that I made to give this demonstration. So we are going to look at flow past this bolt, which is essentially a cylinder, okay. We are going to look at flow past this bolt, which is a cylinder. And so let's set this up, and just a second. Classroom. So you guys should be able to see some lines here of the flow, okay, and I can obviously speed this flow, and these lines look something like this, okay, and then I can slow down the flow and the lines look something like this now, okay. Now notice what happens when I put my cylinder in the flow. So this smoke is coming from this smoke generator, okay. This is basically some this is like a glycol and glycerine solution that is being atomized. So it's not burning, it's being atomized, okay. So now let's look at it. So now if you see the flow, what do you observe? What is the first thing that you observe? What is the first thing that you observe? Huh? Vortices after the cylinder. But if you look at this empty zone downstream of the cylinder, so just probably here, you see what I was talking about, that there is a boundary layer separation that is happening. So right above the cylinder, there is a boundary layer forming, and due to the dp dx becoming positive, pressure increasing as you move further downstream, you see that your boundary layer is actually separating from the cylinder surface. Okay, and you can see this in other type of cases as well. So I can change it and I can put an airfoil in between. So maybe can we switch on the lights temporarily? Sorry, you're visualizing the smoke only. You won't see anything. So the laser sheet. So maybe I can show you what is the need. So you can't see any flow that is happening. So I mean, I'm sorry if I cause some allergies, but that's a hazard, occupational hazard. Even I'm allergic to these stuff. But if you see, you may think there's no flow happening here, but as you can see from here, okay. So all of the smoke lines are being visualized when we do this. Okay, we can put an airfoil in this. We can put an airfoil. So I need some, and then when we put an airfoil, I want to show you that how inviscid theory is not completely useless, because you will see, at least if some of you have looked at the notes, then you will see how it is useful. Can you close this? So I'll hold it. Yeah, no, that's, you have to make sure that you cover it up properly, otherwise the flow will get distorted. It's fine, it's fine. So now let us try to, can we switch off the lights again, please? So now let us see if we can visualize this flow past an airfoil. Maybe I need to. Is it? Smoke's not connected. Smoke's not connected. No. Oh, okay, my bad. So now do you see? Do you see the streak lines that are passing by this airfoil? And if you see, there is absolutely no flow separation past the, as your flow passes the airfoil. But see what happens when I increase the angle of attack or change the angle of attack to something positive, and you see what starts to happen. The flow is immediately separating from the top surface, the boundary layer is separating, and when I put it back to zero angle of attack or very small angle of attack also, you will see that there is no flow separation happening. Now another thing that I want to point out is, if you look at the downstream wake of this flow, if you look at the downstream wake, the moment I increase the angle of attack, you see this flapping of these lines. Okay, this flapping of the lines is actually known as a vortex shedding. Okay, this is called vortex shedding as a phenomena, and basically the aim is to avoid it as much as we can. Okay, when we have a very large angle of attack, for example of an airfoil, then you will see what happens to the flow. So if we have a very large angle of attack, let us say, so basically keeping the airfoil at some absurd angle of attack, is it, has it fallen? Yeah, it's fallen. No, yeah, okay, now it should be sturdy enough. Oh, no, And now look at, can we get rid of the flash? Can we get rid of the flash? So now let's look at what happens when I increase this angle of attack. Oh, that's okay, it will hold. It's not pressing it well enough. So this is your normal angle of attacks, let's say. Now let's see what happens when I increase the angle of attack at an absurd level. See what happens. Okay, and what you see in the wake here is basically a turbulent flow. And this is going to be the progression of our course from now on. We look at boundary layers, we look at boundary layers in different kind of environments, and then we are going to look at instability, which is exactly what you can use to explain this unsteady vortex shedding that is happening. Even though your overall flow is more or less steady, the flow itself, after passing through the airfoil, it is generating this unsteadiness of itself. Okay, where does this inherent unsteadiness come from? It's the instability of the laminar flow. And since your governing equations are still the same, it's the instability of a laminar flow that moves down and gives you turbulent flow. So we'll try to do some more demonstrations when we reach instability and turbulent flow. Okay, maybe we can switch on the lights now.